Hey, welcome. The title of my talk is, If I Unit Test, Do I Need Static Typing? Hopefully you guys are in the right room, and if not, you can run, and that'll be okay. Perhaps an alternative title for my talk could be, Let's put the science back in computer science. My name is Evan Fair. I occasionally tweet. And let me let you guys know a little bit more about me. So I'm a programming language geek. I love studying programming languages. I love learning about the different structures and formats that they have, the different programming language theory that's involved in them. I love academia. But I really love, the thing I love about academia is taking ideas from academia and applying them to real-world software. I'm not content to live in the ivory tower, more like at the basement where it meets the real world. And I love to program. I like to program all of the time. It's my job and my hobby. And we'll talk about something a little bit more interesting now. We'll start with some terminology. Unit tests. We want to make sure we're all on the same page with this. So there is a formal definition of unit test, which is where you write code, and that code tests the smallest testable unit. A small function, a method, maybe a tiny class. And that's kind of the formal definition of it. I've noticed that often we use a little bit more casual definition for unit test. And that is, anytime a programmer writes code that tests other code, we often call that a unit test. Now, I know for some of you it's very important that we use the correct definition. For this presentation and for the experiment I'm going to talk about, we really don't care about the correct definition. People use it casually. We're OK with that. It doesn't really change the results or much with this presentation. This is going to make some of you mad. You can rage email me because I really don't care. Code coverage. So when we're talking about unit testing, we often talk about code coverage. And most often, I've observed that this is in relative to the number of lines that are, or which lines are executed when you run tests. So when you run tests, they're going to execute some lines. If they execute all of the lines of your code, I don't know, there we go. Then, so if this goes blank, just kind of wave your hands, and then I'll know something is wrong, and I'll fix it. So code coverage. When you talk about line code coverage, that means which lines are executed by your unit tests. If you have 100% code coverage, that means that every line of your program was executed at least once with your unit test. And so that's 100% code coverage. Type systems. In programming language, values have types, such as number, string, and list. And the type indicates what sort of operations can be performed on that value, and therefore what operations cannot be performed on that value. A type checker is part of a compiler or interpreter that ensures that only valid operations are performed on values. In a dynamically typed programming language, the type checker runs as the program is executing. And if you try to perform an invalid operation, an error is raised. In some programming languages, variables also have types. The type of the variable indicates what types of values it can hold. Trying to store a value into a variable of a different type is an error. And then static typing is where the type checker runs as the program is compiled or before it is interpreted. And it guarantees that that you will only perform valid operations on your values, and that the variables will only hold values of a given type, and that functions will only turn values of a given type. And if any of these constraints do not hold, your program will not compile or it will not run. And so that's it for terminology. As software engineers, we like to tell stories. Like agile improves quality, TDD or test-driven development increases productivity, many eyes make all bugs shallow, whiteboard interviews aren't effective. The ability to reverse a linked list indicates a good developer. Exceptions are safer than error codes. Solid design principles make code easier to refactor. And dry, or don't repeat yourself, reduces bug counts. And there's a lot more stories we like to tell. About 6 years ago, there was a story about statically typed languages that was pretty popular. And like all good stories, it had 3 parts. The first part was that static typing was restrictive. Now, that's easy to show. Many static type checkers will reject this program and won't allow it to run, even though it'll never crash. So here we have a function called 9. There's an if true, which is always going to be true. And so this function will always return 9, even though there's an else statement there where it could return an object. And that, because there's an else statement that returns an object, would make it so that many static type checkers would reject this. But this function always returns 9. You see down below we call 9 and we multiply it by 5 and everything is fine. So static type checkers can be restrictive, and that's the first part of the story. The second part was, even with static typing, you still need unit testing. And by need, we are talking only about bugs. There's other benefits to static typing besides catching bugs, such as performance. For this presentation, we're only concerned about catching bugs. So for example, your static type system won't stop you from writing a multiply function that just adds its arguments together. So here we have a multiply function. It adds its arguments together. There's a bug. Static type system is not going to help you with that. But a simple unit test will catch that bug. Here we have a unit test that is asserting that 3 times 3 is 9. Then the third part of this story is that static typing is redundant, that when you have unit tests, you no longer need static typing. Once again, with need, we're talking about catching bugs. So I wondered, is this story really true? And I was really curious about this third part, that when you have unit tests, you don't need static typing. Now, theoretically, this is true because you could always write your unit test as follows. So here we have a unit test called test code. And we have part of our unit test, once again, using the casual definition of unit test. We are calling do magic static typing on it, which would do all the things that a static type checker would do if it was built into your language, but it does it as a unit test. But I really haven't seen people do that, at least explicitly like this in their code. So I was curious if this was true for real-world software. So how do you find out if it's true? Well, we go to the source of all truth, which is Google. And this is what we find when you search for static typing is, or in dynamic typing is, and static typing versus unit tests. You find answers like the following. Dynamically typed languages are dead. Static typing makes code not more safe. Static typing is the root of all evil. Static typing will not save us from broken software. Unit testing is overrated. Unit tests are as good as static typing. Static typing has some significant benefits over unit testing. So here we have what appears to be a lot of smart people that have radically different opinions on whether or not this is true, that when you have unit tests, you don't need static typing. So how can we know that it is true? Well, the answer is with science. Ta-da! Kind of reminds me of the Joker and the Batman who's like, ta-da, I want to see a magic trick, so there we go. So I decided to conduct a scientific experiment, and the purpose of it is to answer this one question. If I unit test, do I really need static typing? Once again, we're just talking about bugs. So how do I test this? Well, I could find some code that was in a dynamically typed language and that had unit tests. And then I could do some magic and add static typing. And then I could see if any bugs are revealed by the static typing that weren't caught by the unit tests. And then I would profit, because that's always the fourth step. And in this case, profit looks like this, which means finishing grad school. So this raises the question, how do you add static typing to a dynamically typed programming language? And remember, this was 6 years ago, so TypeScript didn't exist. So this is an accurate to-scale timeline. You've got dinosaurs, and you've got 6 years ago, because I think they're around 7 years ago we had dinosaurs, if I remember correctly. And then you had TypeScript, and now we're here. So I had this idea. What if I took a dynamically typed programming or dynamically typed program, and then I translated it into a statically typed language? And then I count the number of bugs that were caught by the static type checker that weren't caught by the unit tests. Now this part is important. I am not talking about doing a rewrite. Rewrites are fun and exciting. You get to clean up a bunch of code, you get to refactor things, you get to live on the beach and jump really high, the sun's always shining. I'm not talking about that at all. I'm talking about doing something that is not fun, that is really boring. A line-by-line, meticulous translation from one language to another while being careful to preserve the structure and behavior of each line of code. And I had to do it by candlelight like this man did here. It was horrible. So this is not fun. But it seemed worth a shot. So the first step with this experiment was to pick the source and destination languages for the translation. So for the source, I picked Python. It's popular with dynamically typed enthusiasts. It's got a culture of unit testing, lots of open source code to use. By the way, I want to take this moment to thank the Utah Python Conference for having me here today. Just kidding. So the second, for the destination language, I picked Haskell. Now, Haskell is not the most popular statically typed programming language. There's lots of other languages which are used a lot more, but it's considered a good example of static typing by static typing enthusiasts. If I would have picked something like Java, then I could see I would get a lot of negative feedback from people that don't really consider Java to be a great example of a statically typed language, because it probably isn't. So I picked Haskell. So the next step is to find some code. And I have to be careful with how I pick these projects to translate because of something called selection bias. So I'm going to explain what selection bias is with an example. Let's say you wanted to try to figure out what the most popular college in the United States is. And so you go around and you ask these people. Your results are going to be biased because of who you selected. So there's a selection bias. So I had to pick these projects at random because I didn't want to subconsciously pick projects that would give me the results that I wanted or expected. So I ended up picking 4 projects. They are as follows. The Python NMEA toolkit. This is for communicating with GPS devices. MIDI-utils deals with MIDI files. Grapefruit does color space transformations. And PyFontInfo parses true type font files. Each of these projects is relatively small, less than 2,000 lines of code. They all have unit tests. And the second thing I had to be careful about is that I did introduce bugs into the translation or count bugs that weren't caught by static typing. So this is the formula that I used. Now, when I was doing the translation, I found lots of bugs just by reading the code. But if it wasn't caught by the static type checker, it did not count. So it has to be caught by the static type checker. Also, it was possible during the translation that I would accidentally introduce a bug. I would translate incorrectly because I'm human and my computer's made out of meat. So I had to go through and make sure that I could reproduce the bug in the Python code. And if I couldn't reproduce it in the Python code, it wouldn't be counted. So I got to work. And I worked on it whenever I should have been doing this and whenever I should have been doing this. And I'm not saying I did this because I don't want to end up like this, but let's just say I worked on it a lot. And it took about 3 months. So this is what I found. The NMEA toolkit had 9 bugs. MIDI-util had 2 bugs. Grapefruit had 0. PyFontInfo had 6. And these are bugs that were caught by the static type checker and not by the unit tests. So a total of 17 bugs that were caught. And a common question at this point, what about code coverage? Well, if we look at the code coverage, those projects that had 100% code coverage, we see that the only project that did have 100% code coverage was Grapefruit. So we have this weird coincidence where Grapefruit had 0 bugs, and it also had 100% code coverage. So does this mean that with the code coverage caused it to have no bugs or eliminated all the bugs? And the answer is nope. Now you may be skeptical of this. So first of all, let's remember that correlation doesn't equal causation. In other words, just because it both had 0 bugs and it had unit tests doesn't mean that the unit test eliminated the bugs. And I'm pretty confident that it wasn't the unit test that eliminated the bugs because there were other projects that even though they didn't have 100% code coverage throughout the project, they did have functions and method and classes which did have 100% code coverage. And the static type system was able to catch bugs in that code. So if we were to take these other projects and were to write additional unit tests to complete so that it had 100% code coverage, those bugs would likely still exist because they exist in the code that was covered by unit tests. It didn't need more tests. So let's talk about an example of where you can have code with 100% code coverage but still have bugs. So here's a function that returns information about a person's office if they're still employed, and it returns undefined if they're not. So we have get office. We say if person employed, return the person's office, else return undefined. So we need some unit tests for this. So here we have 2 unit tests. The first is for a person that is employed, and the second is for a person that isn't. So you see in the first test get office with employee. We construct a person that's employed. We have employed equals true. And then we call get office on it, and we assert that that equal returns an object that matches the office that that person had. So far, so good. We have a second test here, test get office with retired person. This person is no longer employed, they've retired. And we assert that get office returns undefined. So far, so good. We have 100% code coverage. We have 0 bugs. Everything is good. Now here's a new function that determines whether a person has a window office. Has window office takes in a person. We call get office, and then we call has window on it. We need unit tests for this, obviously. So here's a unit test for this function. We call test employee has window office, and we have a person that's employed. We call has window office, and it should be true. This code will pass, unless if I messed up somewhere on my slides. We have 100% code coverage, but we have a bug. And this bug becomes a little bit more, or so let's look at this code. So if you call has window office with someone who is not employed, like this, and then you call has window office, you're going to see something like this. I'm sure no one here has ever seen an error like this before. I promise you it could happen. An untied error caught with cannot read property has window of undefined, it can happen. It's not just theoretical. It's happened once or twice, I'm sure. This bug becomes clear when we see that get office can return undefined, and has window office is trying to access has window off of whatever get office returns. So how do we solve this issue? Well, of course, we need more unit tests. So let's look at the code that has the bug. Test retired. Before we get to that, so if we had written this unit test retired person doesn't have window office, it would have triggered this bug and we would have caught it. Right? So this is the unit test that we were missing. So now let's look at the original code that has the bug. How can we tell that this code needs a second unit test? So when I look at it, it's not very clear that it needs 2 unit tests. In order for you to understand that you need 2 unit tests, you really need to look at the dependent function. When you look at the dependent function getOffice, you can see that it can return values of 2 different types. It can return an office or undefined. Now this is important. In order for you to know you need a second unit test, you need to know that the dependent function can return 2 different types. And once you know that information, that the dependent function can return 2 different types, well, you're not going to write the bug in the first place, right? You're going to write your top-level function in a way that handles both of those cases. And if you don't know that, you're going to write the bug, but you're also not going to write a unit test to catch the bug. So the unit test isn't catching this bug. You can reproduce the bug, but it is you as a developer that has to recognize you have this scenario and catch the bug yourself. So this example is pretty trivial. I'm sure that none of us would write code like this in the first place. We're not going to make this mistake. We have 2 functions. We can understand them. What about real-world code? Well, I took one of the functions that I translated from one of the projects, and I graphed the different paths that it can take. Now, I removed all the names because it wouldn't fit on the slide. So the top node is a top-level function that would be called. And as all of the lines are different paths that it could take. And so into other functions, and they could each call other functions themselves. So if you wanted to eliminate this sort of style of bug that we've just demonstrated with this example using unit tests, you need to make sure that you follow all those paths, because all those paths could return values of different types that could trigger this bug. So for this top-level function, you need to write at least 38 unit tests in order to guarantee that it's not going to crash in the way that we've just demonstrated. Now, this code looks pretty complicated. When I graph it like this, when I read the code, it didn't seem that bad. I've written code that is worse. Every place that I've worked at has code which is more complicated. When you see the code, it doesn't seem that bad, but when you show up on the graph like this, it seems complicated. So I'm sure that all of us have code that we work with every day that is more complicated than this, and therefore it would take more unit tests in order to catch this style of bug. So code coverage doesn't solve the problem. So what made Grapefruit so special? How come it didn't have any bugs where the other projects did? Well, Grapefruit was written in a style that was unique, in that every function in Grapefruit would only ever return values of a single type. And it was written so that the arguments that were passed to it would only really accept values of a single type. Likewise, every variable was written so they would only hold values of a single type. And when you have all of your code for your entire project written in this style, something nice happens, and that in order to catch this style, this type of bug that we've demonstrated, you no longer need to go and test every single path, because you know no matter which way you call into a dependent function, it will always return values of a single type. And so when you use this style and you use unit tests, then suddenly your unit tests work a lot better because you don't need to follow every single path. You can just test one case and it will catch the style of bug. Now there's other sort of tests you may need to write for other style of bugs, but for this bug, you don't need to follow every single path. So does this style with unit tests solve the problems? And the answer is, well, kinda, but not really. And because this style of coding has its own problems, which we need to be aware of. The first one is that writing your code in this style is error-prone. And it's error-prone in the same way that doing math on an abacus is error-prone. We can all learn how to do it. By the way, this is a machine that people use before computers to do math, for people that don't know what it is. So you can do that. You can do it by hand, but because you're human, once again, we've got these computers in our head made out of meat, we're going to make mistakes, and we're going to get it wrong. Now, we can have computers, and so when we do math, we do it with computers because computers don't make mistakes like we do. And you can enforce this coding style also with a computer, and that process of enforcing this coding style with a computer is called static typing. So you're doing by hand what the computer can do for you. The second, so unless you're perfect and you don't make mistakes, you're going to make mistakes with this and it's going to cause some bugs. The second is that it's restrictive. So do you remember back when you were talking about telling stories and people and proponents of dynamic typing said, well, static typing is too restrictive? Well, we've taken that same restriction that you could get with many statically typed languages and we've dragged it back into our dynamically typed programming language. And so we're facing the same restrictions that you would have with that. So we're not allowed to write code like this, like our 9 function that always returns 9, which is probably okay. You probably don't want to have code like this. But also with this style, you're not allowed to write code like this, where it would return undefined ever, or it would return a string and a number ever. It always has to return a value of the same type. And the third is that it's not practical for larger projects to adopt this style, because it really means that you're probably not going to use undefined or null anywhere. At least you can't store those in variables, because if you store an undefined in a variable, you can't store any other value of any other type in that variable ever. If you have a function that returns undefined, but it can never return anything besides undefined, and the same with null, and all of your libraries and frameworks also have to follow the same restriction, or you don't get the same benefit you would get with static typing. So it's just not practical for larger projects. Now you may be saying, who cares? I write perfect code. I'm going to follow this style rigorously. I'm going to do code reviews. I'm willing to deal with the restriction because I'd have the same restriction with statically typed language. And I'm going to only pick libraries and frameworks that follow the same convention because that's a good thing to do. But this coding style is actually worse than good static typing. And that is, if you were using a statically typed language like Haskell, Elm, Flow, and PureScript, you can safely write functions like this. So this function returns values. Can return an office or undefined. And in those statically typed languages, you can also write code like this. And you can do so safely. But those programming languages will not allow you to write code like this. Because the static type checker would recognize that getOffice could return undefined or an office, and it will force you to handle both of those cases. And so it would force you to write code like this. So here we have our new hand window office. And it's going to get the office and assign it to a variable. And then it's going to check to say, is this office undefined? If so, return false. And if not, it's going to return the office.hasWindow. So these statically typed languages would force you to do this code and thus eliminate the error. And so in fact, these statically typed languages are in fact less restrictive than if you were to try to get the same benefit in your dynamically typed programming language by following this style. And they're safer. So this style of programming is error-prone, restrictive, and impractical. And I've been a little harsh about this, but the good news is that 60% of the time it works every time. And by that I mean that you don't have to translate your whole program into the style of programming. You could do just little bits and pieces of it, and for those little bits and pieces, you would get the benefit of not having this style of bugs in those pieces of code. So for example, you could update your getOffice function to not return undefined, but instead to return kind of a fake office object. Now this avoids the bug in this section of code. And I understand this may not make sense in all cases. Some cases doing this would just be a bad idea. But if you write your functions in a way where possible and where practical to follow this coding convention or this style, you are going to eliminate the chance of having the type error when you're calling this function. And so 60% of the time, it works all of the time. And so I would encourage you to do this. Whenever you're working on your program, if there's a place where it makes sense to use this style versus returning objects of two types or values of two types, do so. It can save you some bugs. So what's the conclusion of the experiment? Well, I'm not saying that dynamically typed languages are dumb and you should never use them. I use them every day. When you're choosing a language, there's lots of considerations to make. You may need to make trade-offs. Engineering often is about understanding constraints and making good trade-offs. The benefits of static typing may be overwhelmed by other considerations. If you have a huge code base in JavaScript or in Python, it may not make sense to rewrite everything in Haskell and Elm. And we also don't want to conclude that what I have done is a proof. In science, we don't get proofs. When people talk about scientific proofs, they're kind of lying to you. We get evidence. Evidence gets stronger as we perform more experiments. And it's possible that I made a mistake when doing this experiment. It's possible that I messed up somewhere. Lots of people have read the paper. I've gotten lots of feedback. People haven't pointed out a flaw in my methodology or in the translation, but it's still possible one exists. It's also possible that there's only 4 projects in the world where unit testing doesn't cover static typing, and I just happen to pick those 4 projects. I don't think that's the case, but it's possible. We do not have proof. We have evidence. So right now we have evidence that in practice, unit testing does not replace static typing. There's one more thing I want to talk about, and that is how people reacted to this experiment as they learned about it. There were 2 common reactions that I saw. They weren't the only reactions I saw, but they were pretty common. One is that my conclusion was so obviously right that I wasted my time. Everyone already knows this anyway, why bother? The second was my conclusion was so obviously wrong that I must have made a mistake. Now, while these reactions seem to be opposite, they do share a common root. Now, yeah, so when you get to the point where you're going to say the word share common root and you put this up there, you've made some seriously poor choices in your life. You really need to consider, you need to go outside, you need to spend time with family, you need to do something else. I apologize, I'm going to get help, I promise. I'll get this taken care of, okay? So they share, where was I? So let's see, same opposite, they share a common root, and that they both dismiss scientific evidence based upon personal experience without providing counter evidence. And I think that's a problem. Because a well-designed experiment can eliminate some of the biases, the logical fallacies, and the rationality that lead all of us as people with meat computers in our head to reach unsupported conclusions based upon our personal experiences. So when we're in a situation where we have both evidence, once again, not proof, but evidence and personal experience, we need to be careful to give more weight to scientific evidence. So think back to the stories that we tell about software development. Is the story that Agile improves quality based upon scientific evidence or personal experiences and anecdotes? What about test-driven development increases productivity? Many eyes make all bugs shallow. Is there scientific evidence to back that up? What about whiteboard interviews aren't effective? Is this based upon scientific evidence? Or do we just have anecdotes that either are or are not effective? Does the ability to reverse a linked list imply that they are a good developer? Is there evidence behind that? Or is it just personal experiences and anecdotes? What about exceptions versus error codes? Or solid design principles? Or the dry, don't repeat yourself principle? And if we don't have evidence, do we really know that those stories are true? Or is your brain just telling you that they're true because it feels good? Think about the practices and methodologies you use at work. Are they based upon your experience or other people's experiences? Or are they based on evidence? And if not, do you really know that they're better? Or is it that your brain's just telling you that they're better because they feel better, or because you like them, or because they're popular and fun? I would like to conclude with a 3-part challenge. The first part, I encourage everyone to look for evidence to support your stories, development practices, and methodologies. Do a search. You can go to Google Scholar. You can search to see if there's evidence to back up those methodologies. Second challenge, is to, if the evidence doesn't exist, consider doing a science experiment to produce evidence. Be careful with how you construct it. Get feedback on it. Make sure you're controlling for some of these things that catch us up, like selection bias and things like that. But do a science experiment and see if you can generate evidence, improve the knowledge of the world so that other people know whether or not there's evidence to back up what you believe. And third, when your stories and methodologies are based upon your personal experience and not on evidence, admit that as you communicate with other developers. Using the following phrases can help a lot. I suspect, or based upon my experience, or it seems like, or I'll believe. All of these communicate to others that you do not know, that you do not have evidence, but that based upon your experience, which can be right sometimes, maybe most of the time, I don't know. I haven't done an experiment to figure out how often I'm right based upon personal experience, but they can be right, but it helps to communicate to others that you don't know. And then maybe we don't need to fight about so many of these things because both sides will admit that we really don't know. So in conclusion, let's go do some science. Thank you. Any questions? So I think we got about 10 minutes for questions. Yes?
Could you contribute back to any of those 4 projects where any of the bugs found things that were like issues already created or things that some of the users were experiencing?
Okay, that's a great question. The question is, I found all these bugs. Did I contribute them back to the project? Well, this interesting thing happens when you finish grad school, and that is you don't want to think about this ever. So and you're just kind of done. So like, I had all these great plans. I'm going to contribute these back. I'm going to like blog about what I learned. And it took me like a year to be able to talk about this, I mean, like, it's kind of a traumatic experience to graduate. And so I have not turned those back. I've published them online, and I've been asked that question many times. And I keep on waiting for somebody to ask me that question to go look online for my name, look for this project, find those bugs, and submit them into the project. And so in some sense, I am not a good community member because I didn't put those back. However, there's lots of people which haven't also found bugs in those projects and submitted them back. So I'm not like terrible, I'm not like Hitler level bad. I'm just kind of lazy level bad. So I haven't done that. Next question. Yes? Was there a common type of bug that I found? Certainly, a bug similar to like calling a method undefined was a pretty popular one in static type languages like Elm and Haskell and Flow and PureScript. That's just not possible. Or if you've used other languages like Python where you reference a none, or like a null pointer exception for people in Java, you just can't do that in those languages. They just force you to not do that. And when you first hear that, you're like, that's crap. There's no way you could do that, but it actually works. And you're thinking like, how do you write code around that? And it actually is like, it works too. You have to change how you write code. So that was a popular one, but they're really just all over the place. I mean, I don't think that there was like 90% of these were this and everything else was in the weeds. It was just like weeds all over the place. Yeah? Have I tried looking at JavaScript versus TypeScript or PureScript? And the answer is no. So once again, when you graduate, you're kind of done. I hope that others would pick this up and do more experiments. I would love to get more data on this. And even trying out like different programming language. It's possible that if I translated these into Java, I would get different results. And maybe the Java type system would find different types of errors than the Haskell one did. And so I haven't done that. I would encourage you to pick it up. If you do want to get serious about this, something to consider, which if I was to do this again, I would do differently, is instead of manually translating this, to write code that could do a lot of the translation automatically. Like if you translated automatically 80% of the code and you had like manually like hand patch up the last 10%, it would have been so much easier than doing this by hand. But you don't learn that until you're 3 months into it and you're just kind of done at that point. So, yeah.
When you began your research, did you look at the landscape of research in this space, and what was that landscape like prior?
Yes, so I did look at the research. That is kind of the requirements before when you do kind of research like this for grad school, you need to go and like talk about prior work, and you need to document that. And I found that it was a barren landscape of nothingness. Like I hadn't seen anybody that had done a project like this. There were things where they were testing like well, if you do static typing versus not, will it make you, go faster, write code faster? There was some stuff like that, or stuff like static typing versus not, speed with that. There was stuff, but never like really static typing versus unit testing. There was there's like books out there talking about it, and there's lots of blogs, people talking about it, and they contradicted each other and disagreed, but like no one had actually sat down as far as I could tell, and they was able to find and done actually an experiment to see whether or not it was true.
Do you understand has the landscape changed much?
It seems like lately that statically typed languages are becoming a little bit more popular, but like we go through cycles, it seems, and so I don't have any. I don't have any confidence that it's becoming more popular because people like read the science and like, oh, this is definitely a good idea, or if they just like, hey, this is something brand new and shiny, and we'll like switch over here because this is a pain. So it wouldn't surprise me if like in 10 years, if people just kind of did the big shift back to dynamic languages because, like, who here has read a scientific paper about programming? There we go. There's like, so there's 4 hands going up, so there you go. So we as a community, we practice computer like witchcraft, not computer science. And I'm not just talking JavaScript, I'm talking like just like programmers in general. That's kind of where we are. I hope that changes. But right now, academia does their stuff, we do our stuff, we don't talk to each other, we yell at each other, but like we don't like learn from it and do anything with it. So, okay. Other questions? Yes?
Did you encounter any bugs that might be susceptible to static programming languages that are not dynamic?
So the question was, did I encounter any bugs that perhaps would be more likely to happen or susceptible in a statically typed language versus a dynamically typed language? I did not. My experiment wasn't designed to catch those, and so I don't have evidence that they don't exist because I really wasn't testing for that, but it's certainly a possibility. I can't think of any, but really when I started this project, I was really surprised at how much, so the conclusion that I reached was not what I was expecting. So I was expecting the other way, and so the fact that I can't imagine something doesn't mean it's not true. It just means that like I have a limited imagination. So, questions? Yes.
So there's kind of 2 questions. One of them triggered by that one. We'll start with that one, and that is your experiment is the way you just described it. Your experiment is actually set up in a way that only tests a certain class of bug.
Yes.
It can only find that certain class of bug as you're going from dynamic to static. It doesn't find a situation where I'm trying to do something in a static language and I can't.
Okay. Yeah.
So that's kind of is that something that you had considered as part of what you're saying, or because I'm not saying
Yeah.
I'm trying to criticize. I'm just trying to is that part of your thinking?
Yes, that's a good question. So one of the things I want to be careful of is that one of the dangers we have with doing scientific experiments is people take your results and they expand it to something that doesn't cover. That was not something I was intending to cover. However, I did make a note that I didn't encounter any code that was written in the dynamically typed language which could not be directly translated over into the statically typed language. So as a side effect, I would say that I found some evidence that that is not common. Now, it's obviously you can write code that cannot be translated over directly. You have to kind of come up with new ways of doing it. But I didn't encounter any of that in these projects. So these projects could have been written from day one in a statically typed programming language, and you wouldn't have to change anything about that. So.
The second question, UtahJS has this, at least as I remember it, because it's been a while since I've written anything in it, you can send messages to objects, and that either does, or you can send a message to null, and it'll just ignore you. Or you send a message to some other object that actually responds to that message, it'll leave you a result back. Which would seem to eliminate a whole class of these type errors because, hey, if the type that the thing is doesn't support that message, I just get back null, which would then chain down the line of, oh, I don't respond to any of your messages, and you still have null down the line. Is there anything about your research that would speak to how many of these bugs this would address?
Okay. So the question was, the question was, in Objective-C, you can have objects to communicate with each other. You can almost think of it like a method call, but they have this feature where if you do this method call on null, it just kind of ignores it and doesn't do anything. So you don't get the crash, but you also don't get the behavior. And so the question was like, do I have any insights or information onto like how much of a benefit that sort of feature in the language would be? In other words, how many of these errors would be eliminated? So not all of the errors that I encountered were that type, or like essentially like the calling a method on a null or an undefined like that. And so it would certainly have caught other errors. So they're handling the null case or the undefined case in two different ways. One of them, in the statically typed language that I use, they force the programmer to think about it and handle it in a way that makes sense to the programmer. The other way is you say, well, we don't want to crash, we're just going to drop this on the floor. I don't have any evidence. My intuition tells me that as a programmer, I would rather explicitly handle that case rather than just saying that like the right behavior is to do nothing. But I certainly don't have any evidence to back that up. But the evidence suggests that even if these languages did have that behavior for nulls, that I would have still found bug with the static typing. So, because there were bugs that were not dealing with nulls that, or the equivalent of nulls that were caught. So that is why.
As in, even if it were another type, let's say it's a number and I'm doing the equivalent of a string concatenation on it, that it doesn't have a method to support that.
Oh, okay. So you're talking about not just nulls, but just generally. So in other words,
I don't support that message, I'll just ignore it.
okay. So the idea is that if you have this message and you were to pass it on an object of a different type and it doesn't support that, the solution is just to ignore that. I don't have any evidence to back that. My intuition, once again, tells me that, but no evidence, so I'm not going to make any claims about that. We are done, so thank you.